Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video, and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. So this is session 16. In this session, parts of DC machine and OCC of a DC shunt generator are the topics covered. So see the figure, this is a DC machine. The outermost part of the DC machine is called the yoke. So here in this figure I will mark, this is the yoke of the machine. So it acts as a protective cover for the machine and it provides necessary mechanical support for the machine. It acts as a protective cover and provides mechanical support. It's made of cast iron or steel. So another important function of the yoke is to complete the magnetic flux path. That is flux produced by the field poles, cut the armature and complete the path through the yoke. This is the direction of the flux. From north it moves to the south through the armature because it has to cut the armature conductors, and through the yoke the path is completed. So like this. So the outermost part of the DC machine is called the yoke. It acts as a protective cover and it provides mechanical support for the machine. It's made of cast iron or steel and it helps in completing the magnetic flux path. So the return path of the magnetic flux is through the yoke of the machine. So in small machine it is a single piece, but in large machine several pieces are assembled to form the yoke. Next is the field poles. So this is a field pole. So this part is called pole core and the bottom part is called pole shoe. Pole core and pole shoe. The particular shape of the pole shoe is meant for more uniform distribution of the flux. That means maximum area of the armature, surface area of the armature should be covered by the field poles. So that is the purpose behind providing such a particular shape for the pole shoe. So from this figure we can make out this is the pole shoe, this is the pole core. So because of this particular shape, more surface area of the armature is covered. So this part is pole core, this is pole shoe. So it is made of cast steel or wrought iron laminations. Now the flux produced by the field poles, it should pass through the armature so that it cuts the armature conductors and completes its path through the yoke. So this actually is a steady flux because direct current is passed through this winding. So the flux produced by the field poles is steady and it is unidirectional. So it's of a steady magnitude, it's of a specific magnitude and it does not alternate. There is no change in direction of the flux. And because of that, it cannot produce much losses in the core, in the field pole. But still the pole core and pole shoe both are laminated in this. In most of the modern machine, both pole core and pole shoe are laminated. So, and because of this, because the flux through the field pole is steady in nature and it is unidirectional, the losses happening in the core are negligibly small. So pole core can be a single piece, but it is advisable to laminate the pole shoe because the armature conductors are carrying current. So it produces a magnetic field around it and the armature is continuously moving. So a magnetic field is moving next to the pole shoe. This can induce an EMF in the body of the field pole, which can circulate a current. So that means which can circulate eddy current. So pole shoe must be laminated in every case, but pole core can be a single uh, piece or it can be laminated either. But in most of the modern machines, both pole core and pole shoe are laminated. So the field winding is placed over this, placed over the pole core. So for example, here it is given. So this is the direction of the current through the winding. So for this particular current direction, this will get a north polarity. So the direction of the current in the next winding, next pole should be adjusted such that it gets south polarity. The next it should be north, then it should be south and so on. So the poles are alternately north and south. We can get the required polarity by adjusting the direction of current through the winding. So these are bolts with the help of which the pole core is fixed to the yoke. Next, field coils. So field coils are normally frame wound on a frame. So it produces, this field coils only produce the necessary magnetic field. Depending on the number of turns of the field winding and current passing through it, it can produce a certain amount of MMF. That MMF divided by reluctance of the magnetic path will give the flux. So for producing a necessary amount of flux or producing a necessary amount of MMF, the number of turns as well as the current through the field winding both can be adjusted. Normally in field winding, the number of turns are many and current through the field winding is comparatively less. Compared to armature current, the field current is less, much less. So the winding is made of copper. So the wire is enameled and it should be of low resistance. So when current passes through it, there is I square R loss in the field winding, I square R loss in the field winding, which is called field copper loss. So we can say for producing a certain amount of flux, the flux density in the core it is a design parameter. So producing a certain amount of flux, the MMF should be adjusted accordingly. So MMF can be adjusted by adjusting the number of turns of the field winding as well as the current through it. So normally in a field winding number of turns are more and current is less. So depending on the direction of the current through the field winding, the pole will get a particular polarity. So that is field coil. Next, armature. This is the armature. What is given in figure is the armature. Armature is made up of laminations. Armature has got slots on its outer periphery. Slots means small grooves through which conductors are inserted. Or these slots accommodate the armature conductors. The armature conductors are connected to this part of the machine. This is called a commutator. This is armature. This is called a commutator. So armature has got slots on its outer periphery to accommodate armature conductors. So the conductors are connected to this part, which is called the commutator. The function of commutator is to make the current unidirectional in the external circuit. Say a conductor which is under the influence of a north pole will have current in one direction, and a conductor under the influence of a south pole will have current in the opposite direction. The armature is continuously rotating. That means the current direction in the armature is reversed in each rotation or in each half cycle. That means current through the armature conductors is alternating. But in the external circuit, we are getting a unidirectional current or a direct current. And that is done by this commutator. So commutator makes the current unidirectional in the external circuit. So commutator is shown separately here. This is the hole meant for the shaft. So these projections are meant for connecting the armature conductors, welding it or making a firm connection. So armature, it's made up of laminations, and that is very much essential. Armature should be made up of laminations because the core loss in a DC machine, major part of it, or we can say the entire core loss in a DC machine is happening in the armature core. And because of that, the armature core should be laminated because the body of the armature is continuously rotating in the magnetic field produced by the field poles. So the field pole produces a magnetic flux and the armature is continuously rotating in that, and because of that, the eddy current as well as hysteresis loss both will happen in the armature core. So the core should be laminated. So the core is made up of laminations, and core has got slots in its outer periphery to accommodate conductors. And the conductors are connected to this part of the machine which is called commutator. And its function is to make the alternating current in the conductors unidirectional in the external circuit. Next, current collection from the conductors, from the commutator, it's done with the help of brushes. So normally carbon brushes are used for collecting current from the commutator. It's like this. In this figure, it is clearly shown. So this is a brush. It is touching the commutator. So the commutator is made of different segments. See, these are segments of the commutator. So between two adjacent segments, there is a layer of insulation. So that the adjacent segments are not in electrical contact. So commutator is made up of segments. The adjacent segments should not be in electrical contact. For that, an insulation is kept in between. So in this figure, there are only two segments which are electrically separate. Insulation is there between. One segment is touching one brush, the other segment is touching the other brush. So when this brush is used for collecting current from the commutator. So the material carbon is used for making brushes because carbon has got a polishing effect. Now, how the current is made unidirectional in the external circuit? One small example is given here. See a single coil rotating like this. This is the north pole, this is the south pole. So this is the direction of magnetic flux. The coil is rotating in this direction. And accordingly, say I'll name this conductor A, this conductor B. Now conductor A has got current direction as marked here. So accordingly, this segment is positive and this brush collects positive current. Or current flows in this direction. From here, it flows to the load. Now, after 180-degree rotation, conductor B comes here. At that time, B will have current in this direction. So, depending on the direction of rotation and direction of magnetic field, a current flows in the conductor in a particular direction, which we can determine by means of Fleming's right-hand rule. Using Fleming's right-hand rule, we can determine the direction of EMF as well as resulting current in the conductor. So in conductor A, now this is the direction of current. Conductor B, the current direction is opposite. That means the current flows like this. From conductor A, it is like this through positive brush. It is flowing through the load and back to the negative brush, and like this the circuit is completed. Now after 180-degree rotation, B will come in this position and the A will be down. So this after 180-degree rotation, this is B, this is A. Now whichever conductor comes here under north pole will have this particular current direction, and accordingly this brush always collects positive current. So this is the function of the commutator. So with the help of brushes, we are collecting current from the commutator, and it is when the armature is rotating, the brushes are making contact with the adjacent commutator. From segment to segment, it is making contact and collecting the current. Now next is the field winding. There are two types of winding. One is called lap winding. The other one is called wave winding. I'll enlarge this figure little so that connection is clear. See? So it's a four-pole machine. The poles are alternately north and south, north, south, north, south, like that. Total there are 24 conductors and four poles. Sorry. Total there are 24 conductors and four poles. So 6 conductors will come under the influence of one pole. So it's marked like that. The conductors are marked. Say 1, 2, 3, 4, 5, 6. First 6 conductors comes under a north pole. Next 6 under a south pole. Next 6 under a north pole. And the last 6 under a south pole. All the conductors under the influence of a north pole will have one particular current direction. And all the conductors under the influence of a south pole will have the opposite current direction. So accordingly, the directions are marked here in this figure. Now these are commutator segments. There are 12 commutator segments, 24 conductors and 12 commutator segments. Now let's see the connection pattern. Say from 1 is connected to from this segment, the commutator segment 1. This is a positive brush. From here the connection made to conductor 1. Then it goes to 8. 8 goes to 3. 3 goes to 10. 10 goes to 5. 5 is connected to 12 and comes to the negative brush. So what are the conductors connected here? So from positive brush, let's start. Segment number 1 is connected to 1, conductor 1. 1 is connected to 8. 8 is connected to 3. 3 is connected to 10. 10 is connected to 5. 5 is connected to 12. And comes to the negative brush. So all these conductors are connected in series and connected across the positive and negative brush. 1, 8, 3, 10, 5 top. So 1, 8, 3, 10, 10, 5 top. 1, 8, 3, 10, 5 top. So similarly, you can trace the other group of conductors which are connected in series coming across north and south poles. So 7, 14, 9, 16, 11, 18. So let's check 7, 14, that is from this negative brush, this is 7. 7, 7 is connected to 14. 14 is connected to 9. 9 is connected to 16. 16 is connected to 11. 11 is connected to 18 and comes to a positive brush. So these conductors are connected in series between a positive and a negative brush. All positive brushes are shorted, interconnected. All negative brushes are shorted or interconnected, and connection is taken to the external circuit. So these two positive brushes, this is the positive terminal of the armature, this is the negative terminal of the armature. So this is what is called a parallel path. So in this machine there are 4 parallel paths. One is 1, 8, 3, 10, 5, 12. Another one is 7, 14, 9, 16, 11, 18. Then 2 more parallel paths are there which you can trace. So this kind of a winding is called a lap winding, and its specialty is that the number of parallel paths is equal to number of poles. This is an important relation for lap winding. Number of parallel paths is equal to number of poles. So the total armature current is divided among these 4 parallel paths. So armature positive terminal 1 is 1, 8, 3, 10, 5, 12. 6 conductors. 1, 8, 3, 10, 6, 12. This is connected to the negative brush. Then 18 like this 18, 11, 16, 9, 14, 7. Third parallel path is 13, 20, 15, 22, 17, 24. 6, last one 6, 23, 4, 21, 2, 90. All these conductors are connected to the positive brush and positive terminal, and these conductors 12, 7, 24, 19 are connected to the negative terminal of the machine. That means the total armature current, say IA, is divided among these parallel paths. So each parallel path carries a current 1, 2, 3, 4, 5, 6. Each parallel path carries a current IA divided by 4. So the total armature current is divided among the parallel paths, and each parallel path carries a current, which is total armature current divided by number of parallel paths. So this particular winding is called a lap winding. Lap winding is meant for high current comparatively lower voltage and higher current machines. There is one more type of winding called wave winding, in which the number of parallel paths is equal to 2. That means each parallel path can carry a current which is armature current divided by 2. So in wave winding, more conductors will come in series. So wave winding is used for higher voltage, lower current machine. Always there is a comparison. The lap winding, higher current, lower voltage. Wave winding, higher voltage and lower current machines. So about wave winding, the only relationship to be remembered always is number of parallel paths is equal to 2, and for lap winding, number of parallel paths is equal to number of poles. So in this example, there are 24 conductors, 4 poles, and 12 commutator segments. These are commutator segments. Now, in a DC shunt generator, there are two types. One is called separately excited. Other one is called self-excited. So separately excited means these are the field winding terminals. I'll mark F of armature terminal A, something like that. So here field winding is connected across a separate source. So field winding is connected to here, in this case connected to a battery. There is a regulating resistance here, a rheostat here and the switch here. So this is the connection of a separately excited generator. So field winding is connected to a separate source of excitation with a regulating rheostat and a switch. Regulating rheostat and switch are meant for plotting the characteristics. Say assume we are connecting a voltmeter here and bring the machine to rated speed. So this generator will be connected to a prime mover. So run the machine at rated speed. Keep the switch open and check the voltage across the terminals of the armature. You will get a small voltage which is called a residual voltage. This voltage is called the residual voltage. This is due to residual magnetism present in the field poles. So even though you remove the switch off the field current, or even though you remove the field current completely, the magnetism will not be completely wiped out. There will be a certain amount of magnetism remaining in the core. It's called a residual magnetism. And this voltage is due to residual magnetism. So this voltage is called a residual voltage. So we are bringing the machine to rated speed with the switch open. We are keeping the switch open. We are running the machine at rated speed and measuring the voltage across the armature terminals, and we get a small voltage which is called a residual voltage. Now, keeping the rheostat in the maximum resistance position, close the switch. Then reduce the resistance gradually. The terminal voltage will increase. And finally, it will reach a stage called saturation. That means after that point, even if you increase the field current, there won't be considerable increase in the terminal voltage. That means the core is saturated. This is field current, open circuit volt, OC volts. This is called the OCC or open circuit characteristics of a DC generator. Now in self-excited case, self-excited case means the field is connected across the armature terminals itself. Field is connected across the armature. Now assume we are bringing the machine to rated speed. Here also if we connect a voltmeter here, you check, you will get a small voltage which is called a residual voltage. Now in this case, how the machine is getting excited is that. So in the beginning, even with the field circuit open, there is a small voltage induced in across appear across the armature terminals, which is called a residual voltage. And when suppose there is a switch here, even after closing the switch, this residual voltage will circulate a current through the field winding. So beginning there is only a small voltage which is called a residual voltage. This residual voltage, when the field circuit is closed, this residual voltage will circulate a small current. Because of that, field is getting strengthened a bit more. That means the voltage across the armature terminals will increase later. Now, when voltage across the armature increases, the field current through the field windings that also increases. That means, so this is a cumulative process. So initially we start with the residual voltage. Residual voltage will circulate a small amount of current through the field winding. That is, field is bit more strengthened. The voltage across the armature increases. That means when the voltage across the armature increases, current through the field winding also increases. So this cumulative process continues till rated voltage is built up. This is how it is happening in a self-excited generator, because in a self-excited generator there is no separate source for exciting the field winding. It is connected across the armature itself. So initially, due to residual magnetism, a small voltage is induced in the armature. So in a 220 volt DC machine, the residual voltage may be of the order of 10 to 15 volts, maybe 10 volts. So this, when the field circuit is closed, in the case of a self-excited machine, this residual voltage circulates a small current. That means field is bit more strengthened. So see, because the field is more strong now, the voltage across the armature also increases. So this will increase the current further, which will increase the voltage further. So this cumulative process continues till rated voltage is built up. So once the voltage reaches saturation, once the field poles are saturated, a further increasing field current will not increase the terminal voltage. So this is called a separately excited generator. This is called a self-excited generator. In a separately excited generator, there is a source meant for exciting the field winding. There is a separate source meant for exciting the field winding. Whereas in a self-excited generator, the field winding is connected across the armature terminals. So this is the shape of the OCC. This is called a residual voltage. This is the shape of the curve. This is the saturation point. So that's all for the session today. Thank you very much for attending this session. If you feel that the session is useful, please forward the video or share the video among your friends. Subscribe for the channel. Also press the bell icon for notifications.